Hello everyone, I'm Liam Hanson. I'm a PhD student here at the University of Bristol. My PhD is focused mainly on isolated propellers in a wide range of operating conditions. So as well as stuff with cylinder turbulence interactions, but I've also done a lot of tilting propeller type tests. So today I'll be talking a lot about that, non-axial inflow conditions, forward and negative tilting. So structure will be similar to NOR's, background, a bit about the experimental methodology, then some of the key results and discussion, and then some concluding remarks. No? So urban air mobility is gaining a lot of attention, and typically these new types of aircraft configurations are being proposed by lots of different companies in industry. They're typically made up of lots of propellers and rotors in a different operator condition to standard helicopters that we've been using the past few decades. So the RPM, the tip Mach number, basically all of the operating conditions are quite different. So we wanted to understand that more to inform design choices and the noise emissions. So a lot of the urban air mobility type configurations are eVTOLs, electric vertical takeoff and landing, and many of them incorporate transitioning the rotors from a helicopter type mode towards forward flight from close to the ground after takeoff. So we know from some results in the literature that we can expect noise changes, loading changes, but there's more work needed to be done to understand that properly. So in non-axial inflow conditions, you can expect it in two kind of phases. You could have it when you take off, hover, and then transition into forward flight. You could also get reverse non-axial inflow, a bit more of an extreme condition, potentially on landing or close to approach to landing. So both of those phases I've investigated, as is normal. So we use both testing facilities there. I won't linger on this, it's been explained, you'll see it later. So this is the second of the tilting test rigs that we've got at Bristol. So like the one presented before, you can go between 0 and 180 degrees, full range of testing conditions. And this is the one with the encoder fixed. So we can do synchronous measurements between hot wire, noise, loading, and know where the blade is in the time domain. So all of it's enclosed. We're using a substantially bigger motor in this one, so it can get quite noisy. So we've enclosed it completely, help stop noise contamination. And this can push up to 12,000 RPM quite easily with a 12-inch propeller. So we can get high tip Mach numbers with more industrially relevant. It also has a cooling system, which I'll show here. So we're using quite a beefy motor. It can get very hot. We have temperature probes fit inside the test rig, so we can get real-time information on the temperature. And then we've got a compressed air system that can pump in cold air to keep the noise, the temperature down to a minimum. And we can run this for a long period of time then when we're doing big hot wire sweeps, so on. And so there's the encoder that's sort of fit inside there. So it's coupled by shaft coupling to the motor, so we can get synchronous measurements with the blade phase. So here's some example photos from the different test campaigns. This is from NOR's tests, forward tilting, edgewise flight. This is in the pressure neutral tunnel. We've got negative tilting, forward tilting today. So to start with the results, this is for a lower tip Mach number case. So it's 5,500 RPM, 12-inch propeller. So we've got SPL spectra plotted against frequency. So it's got that characteristic noise spectra that you saw in NOR's presentation for propellers, dominated in the low frequency range by the blade passing frequency and its harmonics. And then in the higher frequency range, you get more self noise, broadband noise. So the key thing we're looking at here is forward tilting. What's happening when you tilt from edgewise flight or 0 degrees towards 30 degrees to the noise. So in the top left there, I've got static conditions. You don't see many changes at all because there's no flow. But as you increase the flow, you start to see discrepancies in the different tilting angles. With edgewise flight, that light grey, hopefully that's visible on the screen, showing substantial noise increases. So you're seeing more mid-frequency peaks, higher harmonics to the blade passing frequency, and you're seeing broadband levels increasing by in the order of about 10 decibels, even just from a simple tilting. So we wanted to investigate that more. Why is that happening? What's the mechanism? So this is sort of a summary plot. We've got thrust here being plotted against overall sound pressure level. So this kind of summarizes a test matrix for 1 RPM. We've got inflow velocities plotted against thrust for different tilting angles. And sort of the key area to focus on is this top yellow region. So we've labeled that turbulence-induced noise zone. That's where we expect in the upstream portion of the rotor, wake structures being shed and then re-ingested in the back end of the propeller disc. So that's around edgewise flight region where you're seeing that notable noise increase. But how do we know that for sure? Well, we need to look at the flow. So here's some PIV results. So this is the normalized velocity field, and I've got different tilting configurations there. So in the top left there, I've got edgewise flight, the loudest case, bottom right, 30 degrees, which is the quietest case. So if we start with edgewise flight, why is it more noisy? What's happening to the flow? So you've got the flow going across this upstream section and then being ingested in the back end of the blade. You can see an acceleration region here, and the flow is actually being dragged from the front end of the blade into the back end. And you can see that strong wake structure solely at the back end of the blade. What is the comparison of that to forward tilting? Well, you're getting a wake actually in the upstream region, and it's a lot more clean, the inflow. You're not seeing that sort of translation of the flow from the front to the back end of the blade. And we suspect that that's to do with the noise increase that we're seeing. So we know turbulence leads to noise increases, particularly with high harmonic peaks or band increases. So we have to look at the turbulence levels on the flow. So this is the turbulent kinetic energy, or TKE. And just to go through this slide quickly, so on the right-hand side, you've got the inflow coming in, you've got the upstream section, downstream section, so flow is coming from right to left. So if we just look at the upstream section to start with, you can see at the tip region, the TKE levels are minimal between the different tilting cases, not much of a difference at all. As you move in towards the hub, above the plane of rotation, you're not seeing too much of a change in TKE between the tilting cases, but it is increasing. And in the blade plane itself, you're seeing edgewise flight has a higher level of TKE compared to all of the other cases. But if we now look at the downstream portion where we saw all of that flow effects with the velocity field, you can start to see some real clear differences. So the TKE is a lot stronger in the downstream section. And as you move out from the hub to the tip, you can really see a big discrepancy in TKE levels for this light gray, which is the edgewise flight case, and the other cases. So that's showing that that flow that's coming in from the front end of the blade into the back end is highly turbulent, and that's what's likely causing all of that noise increase. So you can see it there. That's the flow being accelerated across. We know that's turbulent, and that's what that noise change is going to be, even just from simple tilting in clean inflow. So we know tilting, even simple, small amounts of tilting can lead to quite substantial changes in the noise, and that's a low tip Mach number. But now we need to look at something that's more towards UAM type scale with higher tip Mach numbers that are a bit more relevant. So this is tip Mach number of 0.56, almost double the tip Mach number of the previous case, 12,000 RPM. And again, I've got different forward tilting angles here. So in purple there, I've got edgewise flight now, consistently the loudest. 30 degrees is the tan there, which is always the quietest. And the clear differences here are, well, one, the discrepancy in the different tilting angles is quite a bit more substantial at higher tip Mach numbers. Even small amounts of tilting are giving 5-10 decibel differences. And those shallower tilting angles are always the loudest. So if we look here, this is 8.66 meters per second, one of the lower velocity cases. You've got a clustering of the shallower tilting angles, which are quite consistently loudest, and then a notable drop towards 30 degrees. And then as that inflow increases, you start to see these higher harmonic peaks, particularly in the edgewise flight case, and drops of up to 20 decibels in the broadband levels from a couple of degrees of tilt. So overall, what effect does that have? Well, I've got the overall sound pressure level here. So just to remind you, that's the integration across the noise spectra, across frequency range. So in the top left here, it's 4.35 meters per second, close to static. Not too much of a difference there in terms of overall sound pressure level. But as you increase the velocity down to 26.5 meters per second, higher mu, you start to see real notable differences in the overall sound pressure levels. It's substantially louder for these shallower angles. And you can see that clustering where you've got from 0 to 12 degrees, noise differences that are quite minimal, and then a big drop down to 20, 30 degrees. So we're seeing quite clear differences just from forward tilting. But now the more interesting stuff with this test rig, the encoder data. So I've got some phase results here. So just to explain quickly what's going on there. Phi here, hopefully that's visible on this screen, is basically the angle of the blade oriented with respect to the velocity that's being pulled into the propeller. So here I've got on the left-hand side a static case. And if you just focus on this 0 degrees and 180 degrees case, that's when the blade is parallel. So in static conditions, if you imagine the blade rotating, you're not going to see much of a difference as the blade moves along. It's static. The flow won't change that much. It's consistent. But if you move into edgewise flight cases, we know from helicopter type theory that you have an advancing and a retreating side and discrepancies in the tip Mach number that you're going to see. So particularly at 0 degrees or 180 degrees when it's perpendicular to the flow, you can have that changes of up to 0.64 tip Mach number on one side, 0.48 on the other. And as you can imagine, leads to a lot of noise, vibrations, the works. So what does that mean in terms of measurable data? So this is the coefficient of thrust, CT. And here I've got it from 0 to 360 degrees through one rotation. So if we look first at the top left, that's close to static conditions. We've got minimal variation in the thrust. That's what you'd expect. The tip Mach number will change slightly, but not too much through one rotation. It's not too bad. But as you increase the inflow, you start to see greater and greater discrepancies as that blade is moving through one rotation with this cross flow, particularly at the low tilting angles in edgewise flight. So you start to see this arisal of these double peaks in thrust and minima at the perpendicular case when you've got the blade basically perpendicular to the flow. So we know fluctuations in loading is intrinsically linked with noise. So what does that mean for the actual overall sound pressure level? So here I've got overall sound pressure level through one rotation. So if I focus here in the top right, this is at 120 degrees. Through 0 to 360, we've got this double peak region. So this is when the blade is actually parallel to the flow. So we're taking the phase overall sound pressure level that we're experiencing through a long period of sampling, and this is giving us the sound. So you've got in the peaks at the parallel case here, but as you increase that flow, one thing to note is you start to see a discrepancy. So you have 30 degrees here at the bottom, and you're seeing a gap in noise of, what's that, 6 decibels. And as you increase, you start to get more and more of these peaks, and these are oriented at the perpendicular locations when the blade is perpendicular to the flow. So quite clearly, there's a link there between the tip Mach number discrepancy, the imbalance in the advancing retreating side, and the noise increases that we're seeing. So similar to the low tip Mach number case, we know that this edgewise shallow tilting angles are a lot louder and definitely worth considering when designing aircraft. So now moving on to the reverse non-axial inflow conditions, so negative tilting, a bit more of an extreme case, but quite interesting. So we've got the far field sound pressure levels here, 11 meters per second here in the top left, and then increasing inflow velocity up to 26.5. So from here, I've got edgewise flight and negative tilting of negative 12 degrees. In the 11 meter per second case, there is a noise increase with negative tilting, but it's not, too substantial. But more interestingly is when you get to higher inflow velocities, you get really substantial changes around the tones. So we're getting a widening of the blade passing frequency peaks at this black line here is negative 12. And that's being redshifted, indicative of basically flow interactions. As we saw with the previous presentation, we're seeing noise increases around the tones, some chopping of turbulence or flow structures, and the broadband levels are changing quite significantly there, 10, 15 decibels at certain frequencies. This is again a higher tip Mach number, and I should have mentioned before, previously we did incompressible type flow conditions. This is now compressible, so you're moving much higher up in the tip Mach number region. So overall, what does that do? What does that mean? So even small amounts of negative tilting, you're getting notable differences in the overall sound pressure level. So even 8 degrees is giving 3, 4 decibels. And as you increase the inflow, that becomes worse. So 4 decibels or so increase in negative tilting overall. But as shown previously, a lot of changes in the tones, which we know are associated with annoyance and other factors such as that. So, seems like I'm on time. To conclude then, we've got a big data set with lots of forward tilting, negative tilting, different tip Mach numbers. This is just, tip of the iceberg stuff with my data set, and NORS. And I've clearly shown here that when you've got edgewise flight and tilting forward, there's a clear difference in what the noise is going to be expected. We know that upstream turbulent weights are going to be re-ingested in the back of the disc for edgewise flight, giving substantial noise increases. And negative tilting is just pretty bad overall. It increases the noise quite substantially. And all of this stuff, in terms of future work, we're doing PIV on to try and dig more into the physical mechanisms, but very interesting stuff so far. So yeah, thank you. Thank you for your attention. If you have any questions, you're welcome to.